So the question is, what do we do with this logarithm thing that we have? Why are we even calling it a logarithm? We define that the antiderivative of 1 over x is the natural log of x, which means that the derivative of the natural log of x is 1 over x. But we kind of cheated because we basically defined this function here, this antiderivative of 1 over x, as basically the antiderivative guaranteed that exists. But it doesn't mean that it's nice or it is anything. But because I call it a natural logarithm, that should have something to do with logarithms. So let's investigate that. Let's talk about that. So reminding ourselves that we define the logarithm as this area here between the horizontal axis and 1 over x, right? Or 1 over t is my variable here. And because we're starting at 1, so when we integrate backwards, we get negative numbers. Okay, so let's look at this logarithm. What if I plot natural log? So let's look at what's happening here. When x is 1, the natural log of x is 0 because the area under the curve from 1 to 1 is 0. And as I went forward, the value of the natural log of x, being the area there, grows, but it grows slowly. And as a matter of fact, when people talk about very slow growth, often they mean logarithmic growth. And when we go backwards, even though we have positive area, we're integrating backwards from 1, so it's a negative, the integral is a negative number, and it blows up because we have an area under this asymptote here as we're going. All right? So let's see, this curve right here, is that what a logarithm curve looks like? Well, let's remind ourselves what logarithms are. Okay? So when we talk about a logarithm, we mean an inverse of an exponential function. What do I mean by an exponential function? Well, you take a positive number, you raise it to x, so that's an exponential number. If this is a 2, and you're looking at 2 to the x, then you're probably a computer scientist. And the inverse of that thing, the thing that undoes it or goes backwards, kind of like square root and squaring, the thing that undoes this thing is log base a of x. Okay, or log base 2 in this case. If I put a 10 here, then you'll recognize probably, if you've got 10 fingers, that you'll recognize that as pH or something. Okay, but we are looking for a natural base here. This is a special logarithm. So what's so special about it? Well, what I did here is I wrote some code, and I didn't hide it this time. I wrote some code here that shows how you get this bar and R. That's not important. What's really important is this part right here. We are plotting a to the x, and log x. In Mathematica, the natural log is so natural that it just, when you write log, it doesn't think base 10, it thinks natural log. So we got the natural log, we got a, and I'm manipulating a here. So when a is right around 1, well, we get 1 to the x, which just kind of stays 1. When a is less than 1, it curves that way. It doesn't look, that's not what we're looking for. Now look what happens when I let a be bigger than 1. Look what happens. Now remember what an inverse function does, what the graphs do. The graphs on the inverse function, if you've got a graph, its inverse is a reflection across the diagonal, where you're kind of switching the x and the y's. So one way of recognizing an inverse function is if their graphs look like mirror images across the diagonal, y equals x. So as I increase the base here, remember this is a to the x, and this is what we were calling the natural logarithm, right? So this is x. So as I increase the base, this looks more and more like the reflection. Now maybe it's 2. Maybe that's exact. Now that looks off. I've got the aspect ratio here set pretty good, so we ought to be able to tell. And that's off. That isn't right. Now 3 is probably too much, right? But look around here. Look in there. That starts looking exactly like a reflection. And of course I know the answer, so I know I'm getting around the reflection there. That's how teachers cheat, right? But there's some number around here where these are reflection, and that's our natural number, which we call E, or the Euler number. So that's the base we're looking for, is that the natural log is a logarithm. It is the inverse function of something called the natural exponential function, e to the x, where e is about 2.71a, blah, 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 blah. It's transcendental. It goes on forever. All right? And to be sure that you understand what that means if you take the natural log of e to the x, you get x, they're inverses. If you take e to the natural log of x, you get x, they're inverses. All right? hope that makes sense. We'll continue next time. Beautiful stuff.